In this video, Dr. Jordan Peterson explains how we adapt to our environment.
I started to introduce all those topics because I was trying to address the issue of how it is that we've come to deal with the fact that things are so complex that we can't deal with them. And so a huge part of the answer to that is the Darwinian answer. One is, well, you keep up with things you can't keep up with by changing unpredictably. So here's an example. You know, sometimes if you're driving down the road and there's a deer on the road, maybe you'll run into it and it'll, instead of jumping out of the way, it sort of jumps randomly and then you run into it. You think, well, that's a pretty stupid strategy. It's like natural selection's at work there, but it turns out that deer jump randomly when wolves are chasing them. Well, why would you do that? Well, because you can't predict it, right? If something horrible is after you, acting unpredictably is actually a pretty good strategy, and that's basically what mutation does. It means the horrible thing that's after you always is the rapid transformation of the environment, and the only thing you can possibly do in that case is capitalize on chance. Okay, so that's one thing. So that's partly why the Darwinian story, I think, has to be right, because the environment does move unpredictably. And the only way you can keep up with something that's unpredictable is to generate variance and hope that one of them has drawn the lucky lottery card. But then there's these additional issues, which is that we also seem to be tightly selected for the capacity to cooperate and compete, so that multiplies our cognitive ability. That's a huge part of it. And then we also seem to have constructed ourselves, so to speak, through sexual choice into these general purpose problem solving creatures. And so we've internalized some of the Darwinian process. So you think, well, most animals will produce variants of themselves physically, and then most of those variants die. But human beings have built a mechanism, let's say, that's like a game engine. I think that's a really good, you know how there are game engines now that people have devised, they're computational devices, and you can take a game engine and you can generate games with it, like computer games. So the game engine is a mechanism for producing games. Well, that's what our brains are like. Our brains are game engines for producing games. And so what happens is that when you think you produce an avatar of yourself, you produce a fictional world that avatar inhabits, and maybe you produce multiple fictional worlds and multiple avatars. That's the you that could be tomorrow, which is what you're doing when you're planning. And you walk the avatar through its potential routes, and those that look good you keep, and those that don't look good you kill. And so then you can embody the ideas that you keep and act those out, and hopefully the idea is that when you embody them, you're successful and you don't get killed. And so when we've been selecting each other for cognitive prowess, we've been selecting ourselves for the ability to generate avatars out of ourselves and kill them instead of dying. It's unbelievably brilliant, and that's really akin to the human discovery of the future, right? The future is a place where variants of you could exist. It's something like that, and other animals don't seem to be able to do that. So we're very sneaky, and well, so far it doesn't seem to be working too badly, although we haven't been around for very long, right? I mean, human beings of our particular subspecies, about 150,000 years, something like that, which is, from an evolutionary time frame, it's nothing, you know. It's 2,080-year-old men. It's not very long, you know, if you think about it that way. Okay, now what I want to do is draw a relationship between that developmental process, that evolutionary process, and the emergence of these underlying motivational systems. It's something like this. So you imagine, you go back in time to the emergence of the development of nervous systems. So there's cells that creatures use to produce motor output, and there's cells that creatures use to map the patterns around them onto themselves, and so that's the sensory layer, so to speak. Imagine sensory layer, nervous layer, motor layer. In simpler animals, you just have sensory motor cells. Then they diversify: sensory layer, nervous layer, motor layer. In fact, that's actually what you consist of when you're first developing in utero. After the blastocyte stage, when your cells differentiate, that's the differentiation: sensory layer, nervous layer, motor layer. So then you think there's a sensory layer. Now what's that sensory layer doing? Think about the world as consisting of patterns of all sorts. Like maybe there's an animal in the ocean and it's being subjected to wave motion. And so its sensory systems map the wave motion onto the motor output. So if you look at a sponge, for example, sponges are good examples because they're sort of half unicellular animals and half multicellular animals. You can take a sponge and run it through a colander and separate it out into cells, say in salt water, and it'll assemble itself back into a sponge. So it's sort of at the, yeah, amazing, eh? It's kind of what you do in utero. The cells somehow know enough to communicate with one another to organize themselves into an organism. It's unbelievable. We have no idea how people do that, because when you're in the initial form, blastocyte form, all those cells are identical genetically. And then all of a sudden they differentiate and they move to the places they're supposed to go. We have no idea how the hell can that happen? These cells are all identical, except for their position. So they're obviously communicating with one another in some unbelievably complicated way and saying, well, you're this sort of cell, and so you're going to differentiate that way. God only knows. But anyway, sponges can do this. Now, a sponge isn't complicated enough to have the sensory layer and the nervous layer and the motor layer. It's just sensory motor cells, if I remember correctly. But what the sponge is trying to figure out is it wants to get water through its pores inside, because that's how it eats. And so there's wave motion constantly, and so what's happening is the wave motion is a pattern, and the sponge is reacting to that in a patterned way. And it's really useful to think about what you're responding to as patterns instead of objects, because we think we react to objects, but objects are actually a specific subcategory of pattern. And so, because it also helps to explain perception. It's like, what does it mean for you to see something? Well, it means a bunch of things, but one of the things it means is, when I look at that thing, it manifests itself to me as a grippable object. I mean, that's built into the way I see it. So if you think about the way that you see that on the surface there, you can tell that it's separate from the surface because it has a bit of a shadow, and it's a different color. And it's obviously shaped for a hand, and so that thing tells you when you look at it that it's a grabbable object. Well, it's hand-shaped, like a stone tool would be. And so, the things around you in the world manifest themselves as patterns of utility. That's the appropriate way to think about it. You say, well, what does this thing mean? Because that's a hard question. Well, one of the things that your eyes do is, like, imagine you've got this representational surface at the back of your retina. It's made out of pixels, roughly speaking, right? Those are the cells. And what it does is map that pattern onto your retinal pattern. And then the retinal pattern propagates itself as a nervous pattern along your optic nerve, and then that manifests itself as a neurological pattern. And that neurological pattern manifests itself as an action pattern. And so the meaning of the object is the action pattern that is mapped onto the percept. And so what does this mean? This is what it means. You think this is a Piagetian observation. It's like one or many. One, right? Because I'm acting like it's one. But if I do this, then it's many. Why? 1, 2, right? They're separably manipulable entities. And so the concept of number is, in fact, predicated, at least in part, on the idea of singular usability. But you're mapping it. It's like, well, what is this? It's a key. Well, what does that mean? Well, I'm mapping that shape into this motion for that action. You say, well, it's not just a key. It's a weapon, right? And so that's because I've mapped it onto a different output pattern. But if you think about perception as the matching of patterns onto patterns, it makes way more sense. You can really start thinking about how perception works, because then you can also start thinking about unconscious perception. So, you know, the blindside experiments show, for example, that if you've had cortical damage, so you think you're blind, you can't see objects anymore, but I show you a picture of a frightened face, you'll show a skin conductance response to it, and you think, well, how the hell can that happen? It's like, I have to see the face in order to infer the emotion in order to have the reaction. It's like, no, you don't. You don't need that at all. You need a pattern recognition system that maps that right onto an amygdalic output that produces physiological readiness. You don't need the perceptible entity, because you think, you see something, and then you think about the thing, and then you evaluate the thing, and then you act. It's like, you do that, but there are parts of you that don't do that at all.
Thanks for watching.